Hey guys, it's Campbell. So today we are going to talk a bit about PID controllers. Now in some of my other videos I've talked about P controllers, or P loops I call them, which are the proportional controllers. Today we're going to talk about the rest of that, which is the ID, or integral derivative controllers. And we're just going to talk about, what they are and how they're useful. This video is going to be pretty basic and entry level, and I'm mostly going to be talking about what I know, which is robotics and programming, and I'm going to talk about how these are useful in those settings. So let's just go ahead and get started. PID stands for, like I said earlier, proportional integral derivative controller. So proportional integral derivative, those are all math related terms. What exactly is PID? Let's think about it like this. If we have an input, here is our input. It is some value. Our input has three modifiers or controllers, which causes it to have a specific output. So here's our input over here, and here's our output over here. And right in the middle here, we have our proportional, integral, and derivative controllers. So for example, the example that I use a lot is, just because it's the one I know, it's motor speed. So let's say that I want my motor speed to be 100 RPM. How am I going to get there? I start at 0. So how do I get from 0 to 100? Well, we got to start with our error. As you probably know, if you've seen some of our older videos, error, I'm going to call error a function since it changes over time, equals our set point minus our current position, or current setting, whatever that might be. So in the past I've used like set point is where I want to be, current is where I am. It's a pretty easy way to think about it. So let's go ahead and talk about how we modify our input. So again, let's say that our input is 100. First, I'll go ahead and write a formula for you guys. So at the end here, my P, I, and D terms are all just going to be added up to one big term. And so for me, maybe that's motor speed, or maybe it is a constant, or I guess not a constant, a variable that I'm going to multiply by motor speed. So really, we'll just call it U, a universal variable, equals proportional constant times our error plus our integral constant times the integral of our error plus the derivative constant times the derivative of our error. And just off to the side over here, alright, ET equals error. So what really does this equation mean? Well, like I said, this term right here, this term U of t, that is just a variable, or a function. It technically is a function because the rest of these are terms. So U of t is a function. I normally use it as a variable that I plug into my functions in programming. And over here we have these constants. They're called K because C is just used too often in math, we have decided. So K of P is our proportional constant, k of I, or sub I, excuse me, is our integral constant, and kd is our derivative constant. Sometimes people like to use kd and kp interchangeably, meaning they just use the proportional constant for their derivative, or they use their derivative constant for their proportion. Most of the time these are separate terms, so today I'm going to just treat them like they are separate terms and regard them as such. So let's just go ahead and talk about these. How are we going to use them? Go ahead and delete this here. I'll keep that little formula up there. So first, let's go ahead and talk about the simplest one, the proportional loop. So it is just a constant times our error. So I'm going to go back to the example of motor speed. I want my motor speed, or my set point, to be 100, but my current position is stopped. My motor is at 0 RPM right now. And error, if you recall, is equal to set point minus current, or 100 minus 0. So my error is 100. So I would just simply multiply 100 by some constant. Maybe I want it to get to 100 quickly, so I make this constant really big, and I say like, 5 times 100, so I'd try and get my motor up to speed real quickly, or I guess rather, my motor velocity right now is set to 0. I want it to be 100, so I'm setting its acceleration to be really quick. So, like I said, proportional is the easiest of all of the loops. It is just whatever your error is times a constant. So easy enough, and I've gone through that in some older videos. Not terribly in depth, but hopefully you have an understanding. So I'll, over on the side here, I'll go ahead and up here make that diagram. So there's my error. Up next is integral. Now, you may know an integral is the area under a curve. If you don't know, an integral is the area underneath the curve. And so normally over off to the side over here, if I have a function, my integral is just this, all of this underneath the curve. Now, unless you have parameters or some mathematical representation of whatever it is that you are studying, for example, if I knew that I want my motor speed to be up here, and I knew that my curve looks like this, then I would be able to say, well, this is, whatever, natural log blank plus whatever. And that's my function. So I could just integrate and that would be that. Unfortunately, for most of our aspects, we don't have a perfect mathematical function to describe our error. So something we can do instead is, let's just go ahead and make a curve, and maybe we don't know what this curve is yet, but it looks like this. What we can do is simply at each of these set points, these markers, whatever they may be, we can just take the error here and the error at, let's say, 0 and 2 and 3, and then we can add all of these up. We get a a good estimation for what our error is, because we are adding this section and this section and this section and this section. And so we can get a good estimate for what our integral is going to be. And in programming, all you'd have to do is just sum what that is at those intervals. But the integral controller is used when your proportional is not enough. You get something what is called, here I'll make another graph right in the middle here. So let's just say I'm starting up here and I need something to get slower. Or maybe this is, let's just call this my error. And this is my time. For some aspects, if you're just using a proportional loop, you will get a line that looks like this. And it starts to flatten out and never really gets to 0. So you still have this much error left, and that is called a steady state fluctuation, I believe. So how do we get rid of this steady state? Well, one thing we can do is use that integral controller. An example where this could be necessary is something like cruise control. That's a pretty common example for a PID controller. If cruise control, if we just had our proportional loop, then we want our car to be a certain speed, and so we start out with our, let's just say we start out with our gas pedal all the way down, and then slowly our gas pedal comes up. In theory though, once we get near that speed, our gas pedal is going to be almost off, and so all of a sudden our error starts going back up. And it will just fluctuate right around here. And it won't actually get to 0. So that's why it's called a steady state fluctuation. Because it'll pretty much just be this distance here between where we want to be, our set point 0, and where we are. So again, to fix this, we use our integral control. So integral is, again, this right here. So let's go ahead and say that our error is 100, our proportional constant is 0.5, so 0.5 times 100 is 50, and then our integral is so here's our graph. We start at 100, but with our proportional constant, we're actually starting at 50, and we start going down. And let's say that our integral is taken at this point. Sorry, you probably can't see that. So right here at 0, and then right here, we can just say that that's 1 second, whatever it might be. So our integral, it's not going to be super precise. It's just going to basically draw a straight line from where it started and where it ended, and it's going to take the integral of this shape. Now the thing with integrals is that because your area under your curve is going to keep growing as your function goes on. Now we're here, now our function is here, and our integral is bigger. As we keep approaching, our integral is going to get bigger until we get to 0, and then it ideally stops growing. So this tells us that our integral constant is going to have to be really small. If our proportional constant is 0.5, our integral constant is going to be something like 0.05. Because if this is going to keep growing, we have to make sure that it is balanced out by a really small constant. Hopefully that makes sense. And then finally, our derivative constant. As you probably know, the derivative is a line's instantaneous rate of change. So if I have a curve that looks like this, a derivative at the derivative at this point is just going to be this tangent line. So again, unless you have a precise and a really well fit mathematical model for whatever it is that you are altering, it's going to be really difficult to be able to get that derivative. So what we do instead is here I'll show you. We do something like this, where here is our output, here is our input, and then here's whatever our controller is. And so our output, let's just say after one loop, whatever it is, we'll call it motor speed again. Let's say that after one loop, our output is now 50. Well, now our input over here is going to run this number, 50, through again. So instead of it just being a, I believe they're called open loop systems, this is going to continue running through. And so instead of having some kind of function and having to find the actual derivative like this, instead we just say, here's our original error, here's our new error. In between them, it could have been something like this. We have no idea, or maybe we do have an idea, but in between them is something like this. Well, we know we can, oh, well, it's not, poor line. The derivative will just be that. And normally when you are running through something like a while loop, it's going to be running pretty quickly. So more than likely, you're going to see a line like this where, you know, it'll barely change. Here are your points, and so, you know, there's the distance between them. It's barely anything, and so you're getting a fairly accurate derivative. And so then it will run it through the output again. Now our output is 25. We put 25 back into the input. It'll run again, and so on. And so now if our previous output is 50 and our current output is 25, we would just do 25 over 50 minus the change in time between them. So it could just be 1. And so our derivative is negative 25. Hopefully that makes sense. The reason you use derivatives is normally to prevent overshooting. So that is fairly common with most controllers. Instead of seeing a real nice curve straight down to 0, which is what we want to see, it'll instead look something more like this, where we come down and maybe we pass it, and maybe it'll fluctuate or maybe it'll steady out. So this is what we normally see. What the derivative controller is intended to do is prevent that. And so instead of fluctuating down like that and going, fluctuating up and down, the derivative controller is meant to just really quickly get that to its position and have it level out. Will that always happen? Yes, of course. Everything that we want to happen is precisely how it works. No, it will not always work like that. So that is why we use these controllers. And then you add them all up at the end here. So with our derivative constant, it really depends on what you're doing. If you are making something that increases in speed, so your function looks something like this. your derivative is going to start getting bigger and bigger, so maybe you want that derivative constant to be smaller. Or if you have a function that approaches something low, then that derivative is going to decrease sharply. Then you want that to be bigger, so it approaches the destination faster instead. It is really up to you. I can go ahead and give an example of what this will look like in code, like I did last time when we did our proportional. So give me just a moment. Alright, so here we are. Let's just go ahead and get started. I've already named my function up here. It's called left turn because I believe I already have turn left. Oh, I have turn right, so I can't use turn left. Fantastic. I'm going to change this to turn left. I just prefer it to be in the right order there. So here's turn left. So what do we have to do first? Well, just like our other ones up here, first we have to call error, or name error rather. So there's error. But what else do we have to do? Well, we know that we have to have a derivative, right? A derivative, it's going to be a variable because the derivative is going to be changing. So let's go ahead and make a variable called d_error for derivative of error. Something else that we're going to have to do, though, to make this a little bit simpler is called previous error, and you'll see why in a second. So we'll make previous error, and we also need to make our integral. Something else we should do is make our actual constants, and we will come back and make assign those values later. And we also have to reset our inertial sensor. So let's go ahead and get into it. We're going to have another while loop, and again it is going to be while our error is not equal to our degrees, because again, degree up here is our set point where we want to be, and error is where we are. So what do we do first? Well, we have to define what error is. So simply, error is just the set point rather minus where we are. Pretty simple. And we also have to make our derivative error. So our derivative is going to be equal to our error minus our previous error. Because again, derivative is the rate of change, and so once we get there, we want to be able to have a rate of change, and to do that we're going to need a previous error and what our current error is, and that will give us what our rate of change is. So now we have to actually activate our motors. So let's do spin forward, and again remember these controllers are the sum of our entire error. So we could just do up here, we could call something like ut, and it equals error plus derivative error plus integral. I'm just going to do it in here. And I will use %. So I hope this makes sense. Because it is the sum, if you recall, then it is going to be current error plus the rate of change of our error plus our integral of our error, and these are going to be multiplied by their constants. We're going to set the constants in just a second. Next we will activate the right motor. Pretty simple. And now we need to make our previous error. So error is just our degree minus our inertial one heading. So at the end of this loop, what we could just do is set it equal to error, because error is degree minus inertial one heading. So let's say my degree is 90, and right now my heading is 45. 90 minus 45, that is going to be 45. So our error is 45. Down here, we're setting previous error to be equal to the error in the last loop, whatever is above it. So previous error is now 45. So when this loop runs again, error is going to be degree minus inertial heading. Maybe that's 44 now, or 46, excuse me. So 90 minus 46. So our error is going to be 44. So our rate of change is now 44 minus 45. Hopefully that makes sense. And then we are going to do our integral, and our integral is just going to add and assign the value of error. So our error is, in our first loop, our error is 45 because it's 90 minus 45, so error is 45. The end of this loop, integral, is going to be plus equal 45. So up here, let's go ahead and set our integral equal to 0. So now when this runs first and our error is 90, our integral is going to be 90. And then it runs again. Now it's 89. So 90 plus 89, there's our integral. Now it's 88. So it is 90 plus 89 plus 88, and so on until it gets to 0. So hopefully thinking about it in this way maybe helps you out in terms of why we need a really low constant for integral. So now let's go ahead and make these constants. For proportional, we'll call it, let's just say 0.8. And then for integral, it's going to be 0.02. And for derivative, our rate of change is going to be relatively low. So we'll do 2. And so now we can just plug these in. Our proportional times our error, our derivative times our derivative, and our integral constant times our integral. And we have to do the same thing down here. So hopefully all of this makes sense. We have to first we have to name all of our variables, our function. Then we have to reset our sensor, so in case we call this function more than once. While our current position is not equal to our set point, then our current position is equal to while our error is not equal to our set point. I just realized I messed this up. It should be while error is not equal to 0. Sorry about that, because error is the difference between where we want to be and where we are. So while our error is not 0, then our error is equal to our set point minus where we are, the distance between where we want to be and where we are. And then I am spinning our motors at a percentage equal to the sum of proportional constant times the error, derivative constant times the derivative, and integral constant times the integral. So that's what it looks like in code. Not as bad as it sounds, I hope. If you guys have any questions about PID and I can answer them, then go ahead and feel free to contact me, leave a comment. I hope that this has been useful. Keep in mind that PID controllers do not necessarily have to be used in robotics to control motor speed. They can be used in a bunch of different ways. They can be used to In robotics, they can be used to set an arm position or maybe a claw position. Outside of robotics, PID loops, like I said before, they're used for cruise control. They can be used for industrial furnaces or ovens to set the temperature. They have a lot of different uses. So I hope that this has been useful beyond just robotics in the event that you need it. And like I said, if you have any questions, let me know. And that is going to be all.